Hello everyone, my name is Ming Yang, and today I will be discussing key insights from the paper Towards Better Evaluation for Dynamic Link Prediction by Poursafaei, Huang, Pelrine, Rabbany. This research focuses on improving how we predict connections in dynamic graphs which evolve over time. We will start with the main idea and motivation, followed by the key contributions of the study. Then we will summarize the key findings and explore the experiment setup and result for TATT plots and negative sampling strategies. Finally, we discuss EdgeBank, a baseline that challenges model evaluation in dynamic link prediction. Unlike static graphs where connections remain unchanged, dynamic graphs continuously evolve, making link prediction a complex challenge. Many existing methods struggle to capture these temporal changes effectively. Additionally, most current benchmark datasets focus only on social or interaction networks, limiting their ability to generalize across different domains. To address this, the researchers introduced 6 new datasets from diverse fields like transportation and politics, improving the scope and robustness of dynamic link prediction models. Another critical issue is the standard random negative sampling strategy, which lacks collision checking and ignores recurring edges. This results in unrealistic testing conditions and overestimates model performance. To better analyze and evaluate dynamic graphs, the researchers introduced 2 novel visualization tools. The temporal edge appearance TA plot, which highlights the proportion of recurring versus newly observed edges at each timestamp, showing how stable or dynamic connections are over time. The temporal edge traffic TT plot, which tracks how often edges reappear, helping us understand the consistency and recurrence of relationships in the graph. To improve evaluation further, the researchers developed 2 new negative sampling methods. Historical negative sampling, which selects edges that were previously observed but have disappeared, testing whether models can correctly predict when relationships end. Inductive negative sampling, which introduces completely new edges that have never been seen before, challenging models to recognize and predict entirely new relationships. Experiment setup and main findings for TA and TT plots. The researchers used TA and TT plots to analyze how different types of edges behave in dynamic graphs. Transductive edges, which are seen both during training and testing, represent recurring relationships. These can often be predicted from past observations, especially when they have a high reoccurrence index and a low surprise index. Inductive edges, which only appear during testing, represent entirely new interactions. Since these edges were not observed in training, memorization strategies failed to predict them accurately. Findings show that while memorization works well for transductive edges, it struggles with inductive edges. This highlights the need for models that can truly learn patterns rather than just remember past connections. The researchers tested 5 advanced dynamic graph models using both standard random negative sampling and their new strategies. The results revealed that traditional random sampling failed to effectively differentiate between methods, often leading to overly optimistic evaluations. Models using historical negative sampling show better performance in predicting when relationships will persist or disappear, while inductive negative sampling provided a further challenge by testing generalization on unseen connections. The findings demonstrated that models incorporating these strategies performed more robustly, proving that better evaluation techniques are essential to advancing dynamic link prediction. The study introduced EdgeBank, a simple baseline that stores past edges without learning patterns. It performs well under standard evaluation, even outperforming more complex state-of-the-art SOTA models. However, its performance drops in harder settings, revealing that some models rely on memorization rather than real learning, highlighting the need for better evaluation methods. Finally, this research improves how we evaluate dynamic graph models, making predictions more accurate and realistic. Thank you for your time.